In this lecture, we study about equivalent circuit of a transformer. Equivalent circuits of a transformer you have gone through in your previous degrees. The definition of an equivalent circuit is it is the lumped multi-port circuit model for the normal power system calculations as viewed from any of the winding terminals with all quantities referred to that winding terminals. So it's a multi-port circuit actually. So from the circuit theory it can be derived. The equivalent circuit can be derived as, say for example, you will have a series resistance and an inductance representing leakage, and then again in the secondary side inductance representing leakage. These quantities are referred to one winding, that is say primary side or secondary side, whichever it is. So this is a typical equivalent circuit of a transformer referred to one of the windings. Now for accounting the core losses, actually here in the shunt branch you see only some magnetizing reactance, but for accounting the core losses we use a resistor also. It is just for accounting. Resistor does not actually physically represent core loss. It is not actual physical resistance, that's what I mean to say, but we use the resistor to represent core losses. So if we account for the core losses, then these series resistance and inductance representing winding parameters. Apart from that, the shunt, you will have that core loss component. This is the core loss resistor, and then magnetization reactance. This is how the transformer equivalent circuit referred to one of the windings will look like. So assuming that all quantities are referred quantities, let us label them. This is Rp, Xp. This is referred values to one of the windings. Either it is primary side or it is secondary side. This is Xs and Rs. So you already know that this is winding resistance representing the losses, copper losses, and Rp, and then Xp is leakage reactance of primary, Xs is leakage reactance of the secondary, Rs is the resistance of the secondary winding. And then here that shunt branch Zm, in this normally Rc it is written core loss component resistor, and Xm. This is the equivalent circuit of a transformer if core losses are to be incorporated. And let us see another way of representing this circuit B. So here we have this resistor here Rb, and club these Xp and Xs together into XL, say XL, and then again the secondary resistor Rs. This shunt branch is divided into two parts. One is here, say Zp, this is Zp, and the other one is here, ZS. Like this. A and B are mathematically equivalent actually. Star delta transformation you can do easily. Here you can see between these three nodes, if you do star delta transformation, you will get equivalent of the both, One is equivalent to other. So both the above AB are mathematically equivalent to each other and equally valid also for a transformer equivalent circuit. But apart from these, we do have approximate equivalent circuits where the primary and secondary parts of these impedances, these RP, XP and XSRAs, these primary impedance and secondary impedance can be clubbed together one side. These are referred quantities, of course, can be clubbed together, and then the equivalent circuit can be either represented like this, for example. So this is resistance and inductance. This is primary and secondary together, and the shunt branch is given here in the beginning. So what is done here, the series branch resistance and inductance, leakage inductance, have been clubbed into one. So this is R, X, and this is Z. Magnetization we can write Zm. Again. So this is one representation. Here actually practically the value of this is 100 to 500 percentage in terms of percentage are 1 to 5 per units. This is this shunt, this series branch impedance is 2 to 10 percentage. Then another way of representing is this way actually, where the series branch comes in the beginning and the shunt branch is put like this. This is another approximate equivalent circuit. So these two, C and D, are approximate equivalent circuits where the resistance R, inductive reactance X are clubbed together of primary and secondary and placed in one place, and the shunt branch is shifted to one other place. So this is again Zm. Here also this is around 100 to 500 percentage. This is 2 to 10 percentage. So the equivalent circuit C and D, though theoretically only approximate, but they are practically satisfactory for most of the purposes. What are the limitations? Let us jot down the limitations here. First limitation is, the main limitation arises from the no load current. Main limitation arises from the no load current. no load current I0 it is written. The equivalent circuit cannot directly recognize the iron losses. See, here we have represented the equivalent circuit, the core loss component of equivalent circuit using this resistor RC. But the equivalent circuit in fact cannot directly recognize the iron losses, but for convenience it is represented by a resistor RC dissipating the same amount of the power. So the RC here is represented which dissipates same amount of the power loss that is occurring inside the core. But it is not physically a resistor that inside the core exists and then that is dissipating that one. Therefore, it is to be remembered that this is not a physical resistance. Means we are using an equivalent circuit, but there is no physical resistance, equivalent resistance inside the transformer body or transformer tanker. So only core loss component, whatever loss is occurring, same amount of the loss will occur in RC. So that is why this is represented for convenience only, but it does not directly recognize the iron losses here. But the specific value of R0 is valid only at the voltage at which R0 is determined by the no load test. So you might remember there are two tests, no load test and short circuit test. Using no load test, the shunt branch components can be determined using no load test, including this RC and XM, both can be estimated using this thing. So this no load test will be conducted at a rated voltage, normally we rated. So in that case, whatever losses occur, that losses, based on the losses, we determine the value of RC. Therefore, the estimated RC value depends on the voltage. Why it should depend on the voltage? Say V by I, R is not constant. Yes, this is not constant in this case because the losses that are occurring inside the core are given by this equation. Pi equals to some constant K1 Bm square and omega square. This is eddy current portion, and plus K2 into Bm to the power of 1.6 into omega. So as you can see, the one is hysteresis, another is eddy current component here. So this is the loss inside the transformer, core loss inside the transformer. Now obviously the Bm is proportional to EMF, or EMF is proportional to Bm. So therefore with the applied voltage, this is approximately equal to applied voltage. So therefore the losses that are occurring in the transformer do not have a linear relationship with voltage. They are non-linear. Bm square in one part and Bm to the power of 1.6 in the other part. Therefore, they are not linearly dependent on the Bm or indirectly on the applied voltage. Therefore, you cannot expect a constant resistance with voltage, the resistance value will change with voltage. Therefore, obviously, the core loss resistance RC, whatever is estimated, is valid only for a particular voltage, for whatever voltage it is determined. Normally, rated voltage will be applied in the no load test. Therefore, the core loss resistance will also be that of rated voltage. This is the second limitation of the equivalent circuit. Then the third limitation. So similarly, just like core loss component of the resistance, X0 also depends on Bm, because the Bm and current relationship is given by hysteresis curve actually, Bm. So it is a non-linear relationship. It is not, of course, to a certain extent it is linear, but more or less it is a non-linear relationship. Therefore, whatever X0, the third point is, whatever X0 that is, X0 means Xm, that is estimated, depends on Bm or on EMF, and which in turn depends on voltage. So this is the limitation. This is the third limitation. But in spite of all these limitations, the first one is no load current limitation, and then the second part is the RC is not constant and depends on the applied voltage. The third one is XM, which also depends on the BH characteristics. In spite of these, the validity, as per the validity of the circuit, even the approximate circuits, lies in the fact that number one, in big power transformers, even in big power transformers, what is the value of I0? I0 is typically less than 5%. It's not, huge. So less than 5% of the total current, and transformers are expected to operate at constant voltage. Second thing is the constant. If the transformers are expected to operate at constant voltage, then Bmax or Bm is almost constant. The voltage is regulated, and then voltage is, the transformer voltage is constant. Therefore, Bm is constant. Under these conditions, I0 plays a negligible role. So no harm done in assuming R core as constant. So there is no harm. Even XM magnetizing reactance can also be assumed constant because of these reasons. I0 is less than 5% and Bm is constant because voltage is constant. Number two point, whether X1, X2 are constant or not. X1 and X2 are very nearly constant and do not depend much on the Bm. Why? Because most of the leakage flux path is in air. Because transformer, what is leakage flux? Here the transformer is there. Then, so this is the winding. What is the origin of this X1 or X2? This is the secondary winding. X2 here. So, if the flux paths are like this, if all flux goes through like this, then the leakage reactance is 0. But some of the flux lines will go like this, and part of the flux path will be through iron, and some portion will leak through the air. each of the winding will be having such kind of flux linkages. They are not mutually linking. So the flux of this leakage flux of primary is not linking the winding of the secondary, and leakage flux of the secondary is also not linking the primary winding. That's why these two windings, these two reactances are called leakage reactances. And will they change? That's what is the question. Will they change with voltage magnitude? Will they change mean not leakage flux magnitude? Leakage reactance value will it change with this magnitude, voltage magnitude? Because most of the flux path is in air, only small portion is in the core. It is almost nearly constant, but however, saturation of the flux density inside, if it occurs, then it reduces the permeability of this iron portion. When it reduces the permeability of iron portion, the leakage flux path, part of the leakage flux path is also through the iron. Therefore, overall permeability of the path will change. Hence, leakage reactances X1 and X2 are also decrease in fact to some extent, not that significantly, it is very slightly. It can be neglected also. So from the practical point of view, it has no effect at all. Please remember, from practical point of view, it has no effect at all. But in fact, it will reduce. If exciting current is neglected, the equivalent circuit in fact is perfect actually. Exciting current is neglected, or if no load current is neglected, the equivalent circuit is in fact a perfect equivalent circuit. So now these resistances and reactances of the windings are clear, I hope, about what is remaining. Okay. Now let us move on to separation of leakage reactances. Now you might have already been introduced about short circuit test and open circuit test, which are not in syllabus now, but of course I will briefly indicate, briefly introduce here. So this is the approximate equivalent circuit like this, and then this is the approximate equivalent circuit. Now this branch is series branch actually, representing winding resistance primarily here, total winding resistance of secondary plus primary, and this is leakage reactance of both secondary and primary, referred to one of the sides, of course, maybe primary side or the maybe secondary side. Referred quantities, please remember, whatever we have been talking until now are referred quantities, not actual quantities. So it is transformed using the turns ratio. Now a short circuit test I will briefly explain. So when the secondary is shorted, one of the windings is shorted, so this is going to be shorted actually. When this is shorted, now what do you expect? Only this branch will be there. Now, as per the ratio of the impedances, just now we have seen, this is 500%, 100 to 500%, and this is 2 to 10%. So this impedance is huge. and huge impedance you are shorting now. Therefore, you can't expect to apply more voltage here. If you apply rated voltage, which in fact has to encounter these two impedances, which is one is 10%, another is 500%, roughly more or less 500% plus will be the impedance here. Now, if you under open circuit conditions, this much impedance will be there. Now, if you short this transformer, this is going to be shorted, then only very small impedance is in direct connection with the voltage source. Therefore, you can't expect a short circuit test to be conducted at high voltage. It is to be few percentage of the voltage only you can apply, less than 10%. 10% of the voltage, very much less than 10% of the voltage you have to apply, and then only rated current you have to allow it to flow through, because at rated current only you are expected to find out the value of R and leakage reactance X. Now, with application of V, small, under short circuit test, some current will flow through. By measuring these quantities, you will be able to find out R and X in short circuit conditions. But remember, this R is total R. R of primary plus secondary referred to the primary, R of secondary when primary referred to the secondary, primary resistance referred to the secondary. Similarly, X is also of both the windings. It is not of a single winding. So how to separate this we will study, that is in the syllabus of this course. Then second one is open circuit test. So this is this is what we do in the short circuit test. Second one is open circuit test. In open circuit test, what will happen? So this is how the open circuit test will be there. Now, here, this is the equivalent circuit. Now, these terminals are open. Now, as already told, this is around 500%. This is around 2 to 10%. Now, compared to this shunt impedance, the impedance of this series branch is very small. Therefore, under no load conditions, when there is no load current like this, in this branch, the voltage drop is negligible, almost zero. You can consider neglect. So, and entire impedance is there here. Therefore, open circuit test is to be conducted at almost rated voltage, V rated. And since impedance is huge, the no load current only will be drawn, and that current is also very small, less than 5% of the rated value. So in this case, using this voltage and then current and then losses which are measured through a wattmeter, and then based on these losses and then these currents and voltages, this shunt branch impedance Zm can be found using open circuit test. So this is OC test, this is SC test. Now in the SC test, short circuit test, the equivalent circuit is simply R, X and then short here and then to the winding. And in the case of OC test, the equivalent circuit can be only consisting of the shunt branch like this. These you have studied in your undergraduate course already. So now here one of the issues here is these quantities R and X are of both the windings. Now how to separate these R and X? Can you think of any test using which you can separation of separation of leakage reactances, say. Leakage reactances. How to do the separation of leakage reactances? Now just go through the equivalent circuit actually. Let us see. You may use this equivalent circuit for separation of the leakage reactances or primary and secondary series branch impedances. This and this I would like to separate, because when we do experiment, the short circuit test, we get them together. Rp plus Rs we will get, and Xp plus Xs. One way is to separate by assuming that both of them are equal, but both the windings are not actually equivalent. Of course, they have one of the windings will have thicker wires and then another one is thin wire. Of course, when you refer it, more or less some balance will be there due to turns ratio and all, but still primary and secondary leakage impedances need not be same. But is there a way by which we can estimate or estimate these impedances separately, or separate out these impedances based on short circuit result from the combined reactances? Can we separate them out? For example, if you have an access to connect some voltage source here, say some voltage source here between these two terminals, say, and if you are able to measure this current I, simply that voltage V divided by I will give me the impedance of this branch. But remember, you do not have access of this terminal. You have access of these two terminals directly, and these two terminals of course indirectly, because there is an ideal transformer here, then the secondary side. This side you have the access to the terminals. Of course, indirectly you are accessing these terminals only. So therefore, only these four terminals are accessible. Based on that, can you suggest some way how can we separate out these impedances, series branch impedances? So I am drawing here the equivalent circuit. The first one actually, this is R1. Now JX1 I will write. And then JX2, R2, even though J is not written here, it is it has to be taken like that only when you represent it as an inductance. Inductive reactance. This is R0 or RC, whatever. JX0, you may say. Sometimes RC and JXM. Until now we have followed that convention only. Okay. So the equivalent circuit is drawn here. Now we want to separate it out, the impedance, primary and secondary. From short circuit test you got, say, R1 plus R2 and X1 plus X2. Now how to separate it out? What kind of connections, what kind of test you suggest? Think a moment and then let me continue. So, suppose these two terminals are accessible, this terminal and this terminal. Suppose if I could connect a voltage source here, V, okay, and then if I can measure the current through this ampere, if I connect voltage source here and measure this current I, then is it possible? What will happen? The current will flow through this and then through this. Assume that this is open. Then again the problem is this midpoint is not accessible. Okay. Again you will get R1 plus R2 plus J X1 plus X2, even if you measure the voltage and current phase. Right? And there will be no current through this, of course, through the shunt branch. So this way also, because this case was suggested by one of the students in your previous batches, that's why I have considered here. So you may be getting any other idea. Just think over what to do, how to get the separate impedances of primary and secondary using some external connections through accessible terminals. Meanwhile, you think about it, I'll draw the equivalent circuit once more. X1 or JX1, JX2, R2, X0, JX0. It's okay. Even if you don't write J also. It's a representation, it's not an equation. Now if suppose I connect a voltage source like this, V. Now I need a impedance of only one of the branches, because combined impedance is known. Combined impedance of these two, this plus this, is known using short circuit test, where R1 plus R2 and JX1 plus X2 I have already obtained using short circuit test. Now we want to separate these two. So in order to separate, for example, we connect a voltage source like this. If we connect a voltage source and say we are measuring the current I, if we connect a voltage source here and measure a current I here, then what we will get? We will get the current and and since this is open, more or less no load current will flow because this is huge impedance is coming into picture. But somehow if we know the voltage across this R1 plus JX1, obviously the voltage and current are known, therefore the impedance can be known. Can we measure that? Yes, it is possible. Here I will connect a voltmeter. This voltmeter like this. Then this voltmeter reading is simply voltage across this primary branch R1 plus JX1. Am I correct? Just think over. Will there be current in this branch? No current because secondary is open. Since there is no current, the voltage drop in this is 0. Therefore, this node potential and this node potential are same. Therefore, the voltmeter reading is simply the voltage across R1 plus JX1. Therefore, the voltmeter reading Vm is simply I naught, because the ammeter reading is no load current reading only, into R1 plus JX1. So from voltmeter reading and ammeter reading, so this is not the voltage source voltage, please remember. If you use voltage source voltage, then you will get this branch, not the voltage of this one. So using these, now R1 plus JX1 can be obtained by Vm by I naught. Right? So this is how the impedances, series impedances can be separated. If you know one primary series impedance, then obviously the secondary series impedance can be obtained by subtracting the primary series impedance from the total impedance actually, which is obtained using short circuit test. But there are practical difficulties actually. How do you implement this practically? Practical implementation. You have a transformer. How do you access these two terminals? That is very important. Because the current, the voltmeter voltage has to be, this node potential has to be equal to this node potential. Right? This happens only when you have some additional equipment. For example, here actually this terminal is not directly accessible. You will have some ideal transformer as already told to you, and then these two terminals are accessible. But remember, this terminal is not at the same potential as this terminal because of the turns ratio problem. But you need the potential of this point. I will use potential of this point and this point to be same, because you are accessing the voltmeter connection here. But if you go to the transformer, actual transformer, here this is referred quantity actually. Here this side is not accessible directly. So you can only access this point. Of course, this is ideal transformer here, this at the end. So how to access this one? So in order to practically realize, you need one more transformer. So how it is connected is this. Practical realization in a transformer, you need actually a potential transformer which will be having similar ratio. For example, if this is n:1 ratio, you need 1:n ratio. So the practical realization is done like this. So here this is the transformer. Now what is done is, so I am drawing 1, 2, 3, 4. Okay, these are 5, 6. Here ammeter is to be connected here, and then the voltage source is connected here, V AC. Now this is the transformer secondary. Now we will have to connect one more transformer like this and raise the potential, because you are having access to these 5, 6 points only. This 5, this is 5, this is 6, and then you have to raise the potential to say 3 dash and 4 dash. 3 dash is having exactly same potential as 3. Therefore, you can use 3 dash to connect this one. Now this is 1, this is 2. Now here you connect the voltmeter like this, voltmeter like this to 3 dash, and then the primary of this should be connected to this in order to have same level at this 4 dash, because all 2 and 4 are at same potential. So therefore 2 and 4 dash are connected here in this circuit. Therefore in this circuit also we have to connect them. This is n:1 transformer. This is this is n:1. This is 1:n. So like that. This is potential transformer. This is actual transformer. Actual transformer under test for which we are finding equivalent circuit. Okay. So this is how the separation of impedances can be done. But there are some practical difficulties here. What is the practical difficulty? First practical difficulty is to get a matching ratio of potential transformer. See, not all potential transformer are having the same ratio as you require. So a matching potential transformer PT of matching ratio is first difficulty. And the second thing is, the no load current contains a good deal of third harmonics. Now we are calculating the impedance using this formula, right? Vm is equal to I0 into I0 into R1 plus JX1. But this I0, if it is of single frequency, then we don't have any problem. But it has good amount of third harmonic component. That complicates it. Then what is the third difficulty? The equation V equals to I0 Z1 holds only for fundamental components. Holds for fundamental components of V and I0. It doesn't hold for third components. That is the another difficulty. So therefore, these are the limitations of separation of leakage reactances using this kind of test. We will discuss another test known as series opposition test in our next class. Thank you.